Identifying unknowns. Topic is often called analysis. So we're going to deal with that, and what it's concerned with is identifying chemicals where you suspect they're a certain chemical, or having no idea what the chemical is and trying to find out what it is. So let's get into the topic. Let's understand the difference between a chemical test and a physical test. Any small procedure in chemistry is referred to as a test. So when you do something, it's like that we refer to it as a test. So the test for hydrogen, for example, that are probably the most famous of our tests, is that you take the gas, light it with a splint, and if it gives a squeaky pop, it's hydrogen. Now that small procedure is termed a test. Now there are certain tests in chemistry that rely upon reactions. That's where the bonds within the compound are broken, and we observe something and new things are made. And that's a chemical test. It relies upon reactions of that thing happening, as opposed to a physical test where it's not a chemical reaction. It's like we look at density, or we look at boiling points, or we look at diffusion rates. It's where the chemicals stay as they are. There's no change to the chemicals per se. It's not a reaction. And we are going to look in the topic at variety. We're going to look at some chemical tests, and we're going to look at some physical tests. So just to give you an example, so you know the difference. Oh, right there, that's that hydrogen example I talked about. So squeaky pop test is a chemical test because it relies upon a reaction, and the particular reaction it relies upon there is the reaction with oxygen, and hydrogen and oxygen make water. It happens so very quick that we hear a squeaky pop. It's very common. People tend to know the hydrogen test. Test for water. Well, you might boil it and see if it boils at 100 degrees. And that is a physical test. I know you might argue that the water's changing to steam, but water, liquid, and water, gaseous, water and steam are the same chemical. It's just the gaseous version is called steam and the liquid version is called water. So understand the difference between chemical tests and physical tests. Let's get into the tests that you need to learn, and these are the ones, just learn them parrot fashion. So to prove that you've got some water present, what you need to do is to get white, solid, anhydrous copper sulfate. And when you put your chemical that you think may have some water in it, when you put it with this white anhydrous copper 2 sulfate, then we see the white colour go blue only if there is water present. Without water, it won't go blue. I've talked about this test in previous videos, and I've demonstrated it. Now, that will work. Say we've got impure water. That will work. That some water present test. But sometimes we want to prove we've got pure water. That does not prove pure water. What proves you've got pure water is it boils at 100 degrees and freezes at 0 degrees. So what you might do as a test to prove you've got water is boil it. Boil the liquid. If it boils at exactly 100 degrees Celsius, then it's pure water. That's a physical test. So that's what you do to prove it's pure water. That's what you do to prove you've got some water present. An amended version of that boiling point of water is to use the melting point of water, or if you freeze the liquid and the liquid freezes at exactly 0 degrees Celsius, then it's water. So that line uses boiling points, the bottom line uses melting points. Either of those you can use, but most of the time my pupils write about the boiling point of water being 100 as the proof that it's water. Let's get on to some other things you need to prove. Hydrogen gas. Take a test tube of the gas and light it with a splint. A splint that's lit, a splint that's burning, a lit splint. If you hear a squeaky pop, then that is proof that the gas was indeed hydrogen. Learn that. In the same way, what's the test for oxygen? Well, here you don't take a lighted splint. You blow out your lighted splint and then it's a glowing splint. That's the thing to focus on. We've got a test tube of the gas, get a glowing splint, and you must write the word glowing into this test, and the glowing splint will, when you put it into the test tube, when you put it into oxygen gas, a glowing splint will relight. And the relighting, if the splint relights, then that's proof that the gas must be oxygen gas. So I want you to learn that. I want you to learn the test for hydrogen. I want you to learn the test for oxygen. In fact, all of these tests, all of the tests in this topic, I want you to learn. You need them for GCSE. So, test for carbon dioxide. Get some lime water in a test tube. Put what you think is the gas, carbon dioxide gas, put it into that test tube. Put your thumb over the top and shake it up. Or get your test tube of lime water and bubble the gas, bubble any gas through the lime water. Basically, we're trying to react lime water with the unknown gas. And when we do that with lime water, if it's carbon dioxide, then a reaction happens, chemical test, and the chemical made is calcium carbonate, which is a white solid. And when you see the white solid, it looks milky, or what I want you to say is you get a white precipitate. So let's read what I've written there, and I want you to regurgitate that if necessary in an exam. Take a little lime water, bubble the gas through the lime water, or you can shake the gas with the lime water. If you get a white precipitate, then the gas must have been carbon dioxide gas. So that's a test for lime water, carbon dioxide, learn that. Now, two other gases that you asked about are chlorine and ammonia. And learn these two as well. Chlorine is a test which proves you've got chlorine if you take blue damp litmus paper. Now, it needs to be damp so that the chlorine can dissolve into the paper and react with it. So damp blue litmus paper, if you put it into the gas goes into the paper, and first the paper is seen to go red for about 1 second. It goes red because chlorine is acidic. But having gone red, then it's bleached white. The bleaching action, the specific reaction of hypochlorite ions or chlorine in water that makes ions, those will destroy a lot of the coloured dyes, and consequently when they do so they bleach the paper, and if those things happen then the gas must have been chlorine gas. So learn damp blue litmus paper, put it into the gas, watch for a momentary red coloration, and then that paper going white, being bleached, is proof that the gas was chlorine gas. Now finally, ammonia gas. Now this is not a test that proves you got ammonia, but at GCSE we use it as such. We use it where we want to prove ammonia, but really, if I take you through it, all it really proves is you've got an alkaline gas. But at GCSE, the only alkaline gas is ammonia, so we use it as a test for ammonia when it's strictly, it's just probably ammonia. So let's see what the test is. Take some damp red litmus. Now start with damp red litmus, put it into the gas. That damp red litmus, when the gas goes into the dampness on the paper, the damp red litmus will go blue because it's an alkaline gas. And the alkalinity points you towards ammonia. So learn those two, and that makes like 5 gases. Now if I go back, water and the 5 gases, learn those. This topic though is more about ions than it is about water or gases. I want you to learn the water and gases, but I want you to focus more about ions. And if I just cover that up by standing in front of it, and I need to make some very common logical ideas so that they get into your head. Say you've got an unknown. Now this green powder, unknown. But what they will say in this topic is the compound is ionic. Or you will know it's ionic if it's a combination of a metal reacting with a non-metal. So if I tell you this is ionic, this green powder, and I want us to test, to do simple procedures to prove what's in there, then this is what this topic is about mainly. It's about take ionic compounds and find out what they are. And the basic ideas that we need to develop, that you need to understand, is that the unknown, being ionic, will be made of positive ions and negative ions. Positive ions and negative ions. Now, if we can identify which positive ions, like copper ions, and which negative ions, like sulfate ions, then we know the compound will be copper sulfate. Now, this is not copper sulfate. This is something else. So how do we find out what this is? Well, focus on the ions that make it up. We're going to try and find out what the negative ions are, going to try and find out what the positive ions are, and then together we'll be able to use logic to say that this compound is whatever it is due to the ions that make it up. Now the problem with ions is that the ions here are in a three-dimensional framework. If I just take some of the solid using a spatula, there, and I'll put some in a beaker, those ions are not freely moving about in the beaker, because solids, the ions are locked into their positions. They're vibrating, but they're locked into a three-dimensional lattice of positive, negative, alternate ions in 3 dimensions, and they might be vibrating, but they're not moving around. Now we need the ions moving around. So I've got some water here. If I put water, sorry, I'm squirting water. Hope you see that. Squirting water into my beaker, and then I stir it up. That process of dissolving, if the ions separate from the solid, then that solid will dissolve. And when that solid dissolves, then the ions are free. And the ions are then moving about. So there, the ions are freely moving. How do we know? Well, there's no solid left anymore. If you look in that, you can't see any solid. No solid. You can see through it. It's transparent. And if you watch my previous videos, that's what we look out for when we're checking whether something's dissolved. So we need to dissolve our ionic compounds. We need to dissolve them in order to get the ions free that we can then do the tests that I'm going to teach you in a minute. So dissolving. And most of the unknowns that they give you at GCSE will be soluble ionic compounds. Ionic compounds are soluble, and then what you do is you dissolve them. Having dissolved them, it's called a solution. You take a solution of the unknown, and then we can do a lot of our tests, which I'm going to show you some of those today. There are three parts to the sequences we're going to go through. I am today going to do reactions of sodium hydroxide, but then there are flame tests, and those two, reactions of sodium hydroxide and flame tests, those two identify the positive ions, and then we have other simple tests we do to prove what negative ions we've got. So there are three distinct sections I want you to learn, and in this video I'm only going to deal with the first. I'm going to deal with reaction with sodium hydroxide, and I hope you understand that we need to start with solutions. So I've got some there. We're going to start with solutions. What solutions do we need? And actually, I haven't been through these. Let's just check. I've been through these points. Ionic compounds are made up of ions, both positive ions. Now, positive ions are called cations. Negative ions are called anions. Cations, anions. Learn that. Later, when we do electrolysis, we use phrases like cathode and anode, and that's where these names come from. The positive ions go to the cathode, the negative ions go to the anode, and that's why they're called cations and anions. Don't worry about that yet. I'll teach you that later in a future video. But you clearly need to know ionic compounds are made of positive and negative ions. We did that back in year 9 chemistry. We carry out tests that prove the presence of specific ions. And then we know what ions are present. We can use logic to work out what the unknown chemical actually is. Usually, ionic compounds are made of just two ions. A set of positive ions, say magnesium, a set of negative ions, say bromide, and therefore logic tells you that the binary compound is magnesium bromide. Now, there are ionic compounds that have more than two ions, but they're rare, like potassium aluminium sulfate, sodium hydrogen carbonate. But a lot of the things that we talk about have just two ions: magnesium bromide, sodium hydroxide, lead sulfate, iron 3 nitrate. See, they're all binary. They're just positive ions with negative ions. If we learn the test for the ions, then we'll be well on the way to identifying what it is that we've got. So, to identify positive ions, we are going to use that reaction today. I'm going to demonstrate those. That's the reaction with sodium hydroxide. Now, this is sodium hydroxide. I'm going to use sodium hydroxide. Solution. It's been dissolved in water. Sodium hydroxide is a white solid. Dissolved in water, that is sodium hydroxide solution. So we've got sodium hydroxide solution, and we're going to add a few drops of that to our unknown, and we're going to look to see if we get a reaction, and then we're going to add loads. When we add loads, we say excess, and having added a little, can you see that? Having added a little sodium hydroxide, and then added loads, then when we record the observations, from the observations, specific ions react in a very specific way, and if we know and learn our tests, then we can identify certain ions. You cannot identify all ions like this, but you can identify some of them. And I'm going to go through the ones that you should be able to identify. And there are many that we cannot identify. And the many we cannot identify like this, then we move on to doing flame tests. And some of those that we cannot identify, with a flame test, we can now identify some of those. But at the end of A and B, at the end of those two tests, there are still many ions that we just cannot identify. And that's fine. In an exam, they'll only expect you to be able to identify ions that we're going to deal with in this section. They're not going to ask you to identify ions that are not in this section. So I'm not going to do the flame test section this time. I'll come back to it. I'm going to do it on the next video. Otherwise, this video will be too long. So with sodium hydroxide, you need a table like that. We're going to be able to identify some of these. We will not be able to identify all of these. We are going to identify some of those ions. And the way we're going to do it is we're going to observe what happens with a few drops of sodium hydroxide. And then we're going to observe what happens with loads of sodium hydroxide solution. And we're going to fill in the table, and I'm going to tell you which are the characteristic tests, which ones to learn, and which ones will identify these ions absolutely. So let me just pause it and move you to my test tube. Okay, so I've got my chemicals lined up here. The first chemical is that green powder that I was using earlier. Remember, we dissolved it and made a little solution. This is iron 2 sulfate. The same water is just like water crystallization, but it's got iron 2+ ions within it, and it's got sulfate ions within it. The two ions in this are iron and sulfate. So if I dissolve it, and there I've done that, I've dissolved a little of this into a little water. A few grains I've dissolved into a little water. That's a boiling tube. I'm then going to do the test there with what happens when you take sodium hydroxide solution, and you put in a few drops. So that's a little. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 15 drops or so. And then I want to show you. Look. That is a green precipitate. You can see the green solid. You can see the green solid being made. And then the second part of that table was, what if you got loads? And I'm going to put loads by just pouring loads from a bottle in. And showing you that with loads, the solid remains. There's no extra change with loads. So there's only one solid. There's only one solid that will give you a green precipitate with a little sodium hydroxide. And then that green precipitate will stay, and no further reaction will happen with loads of sodium hydroxide. And that is the proof of the ion called iron 2, Fe2+. Take that out and look at iron 3+ ions. So how do iron 3+ ions react? I'm going to do exactly the same thing. I'm going to just take some drops here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 drops, and show you that you get a white precipitate. I'm going to put more in because the precipitate is not immediately obvious. So let's put more drops in. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15 more drops. Now you can see the solid. If I shake it up, I'm hoping you can see solid bits. Let me show you I can probably show you solid bits by putting more of this in. Squirt full. And then we need to add loads. Now if I get loads and pour it in, there's no further change. You should be able to see that this is brown solid. Maybe if I clamp it there and move this to show you like that. You see? You should be able to see the brown solid in there. We call it a brown precipitate. Brown precipitate. So again, with this one, let me just tighten that stand. So there's only one ion which will give you a brown precipitate, and that brown precipitate will remain, it will remain in excess, sodium hydroxide. And that ion is iron 3 ions, like Fe3+ ions. Okay, let's move on to the next ion. Copper. Copper ions, copper 2 ions. Now copper 2 ions in water are always blue. That's why this is blue. Copper 2 ions. What we do is we get a little, like some drops there. Show you that that is solid. You can clearly see the solid. Blue solid, blue precipitate, and then with loads, it remains. With loads of sodium hydroxide, the blue precipitate remains. And that blue precipitate remaining is proof that you've got copper ions, copper 2 ions, Cu2+ ions. So Cu2+ ions will give you a blue precipitate, and that blue precipitate will remain. Well, next I've got magnesium. Now these are magnesium ions. With magnesium ions, you should see a white precipitate. See that? White, solid, white precipitate. And with loads, that white precipitate will remain. I know it seems as though all of these are, why are we putting in loads when we know it's going to remain, but there is one ion where it does not remain, and you need to know it. And that's why we go on and on about all of these precipitates, they remain. Now, magnesium ions do that. Let me just put that back in there and do calcium ions for you. Calcium ions. In the same way, we're going to just put a few drops. And we get, believe it or not, we get a white precipitate. You can see the white solid. White precipitate. Put more in, get more of that white solid, and then put loads in. And that white precipitate remains. Look, it remains. You cannot see through it. It does not redissolve. It remains. But can I bring you back to, that was magnesium. That remained, and it was a white solid. Calcium is a white solid, and it remains. And there's no real observational difference between the two. So, magnesium ions and calcium ions, you cannot identify because they have the same outcome. What really we want for a test to do, if we want a proper test, we want the tests to be giving us different answers for the ions that we want to prove are there. And if they give the same outcome, then that's not good for us. Like, there's only one ion that will give me a blue precipitate, copper ions. So that's a good test for copper ions. But if we want to test for magnesium ions or calcium ions, then this test, this little procedure of adding a little bit of sodium hydroxide and then loads, is not good, won't work. We cannot identify magnesium ions and calcium ions doing this test. That's what I said to you. You cannot identify all the ions that you'll come across. You can only identify some of the ions, and we talk about those. Now, this next one's quite important. Watch what happens here. This is potassium ions. Potassium ions will, with a few drops, give you nothing. No precipitate. Look. You see through it. That is no reaction, no precipitate, no observable change. And then when we add loads, we get no change. There are many ions that won't react with sodium hydroxide. Potassium ions are one of those. There are many ions that will give you white precipitates. There are many ions that do that as well. And ions that give you a white precipitate, or ions that give you no reaction and a colourless solution ends up, then they're no good at identifying those ions either. So it's important to know white precipitates or no reaction completely. There are many ions that do those, so they're not good. They're not good at identifying anything. The next ion, this is the one that will have a change with loads. Watch. So we're going to put, actually let me tell you what it is. That's what I did with the others. Aluminium ions. This one is aluminium ions. Let's just put some drops in and we'll get a white precipitate. See that? Let me show you. See that white precipitate? Having got your white precipitate, then what about loads? Well, let me get loads of sodium hydroxide. I've got loads here. And put it in. See, I'm getting more and more white precipitate. But eventually, that white precipitate with loads will redissolve. Watch. I'm going to put my thing over the top, turn it up, side down, turn it back. And I'm hoping by the time I've done that, all that solid has dissolved away. So with loads of sodium hydroxide, the aluminium hydroxide dissolves away. Now, I'm going to show you theoretically what happens in these reactions when I carry on my PowerPoint. But this is the one that gives you a white precipitate with some drops or a little sodium hydroxide, and that little sodium hydroxide redissolves. It redissolves in loads of sodium hydroxide. Can you see? This is the reason we add loads, because there's only one ion that will give you a white precipitate that will then redissolve in loads, and that is aluminium ions. So aluminium ions, these ions, aluminium ions do that, and it's a very good test. We can prove we got aluminium ions, Al3+ ions, by doing that. Now the final test is ammonium ions. Now we need to add sodium hydroxide, and here we'll add a little, and we see nothing. It's a bit like potassium ions. There's no observable change. We add more, no observable change. Let's just add a little bit more. There's no observable change. So why am I doing it? Well, there is a small procedure we can do with ammonium ions that proves we've got ammonium ions, and I'm going to show you that in a minute. I'll move that away. We just pause this while I light the Bunsen. Okay, so I've got Bunsen burner, and this is my ammonium ions here that I added sodium hydroxide to, and nothing seemed to happen. Well, if I just angle that and get heating it, make it hot, and then I've got some red litmus paper. I'm going to dampen it, so I've just put it under a tap, and I'm going to hold that there. See it go blue? Let me just show you that again. Maybe I can get this closer. See it that way? So when you've got this kind of thing going on, and your red litmus paper has gone blue, then you know the gas is alkaline. And if it's alkaline, that gas is ammonia. And the only ion to give you ammonia gas is ammonium ions. Right, so I've been through these ions. Ammonium ions was the one where I've just been holding up some damp red litmus. What do you need to learn? You need to learn the following observations. I've put them in. Yeah, I had problems with the next slide, so hopefully I'll get it now. These are the observations you need to learn. Iron 2 ions give you a green precipitate. Iron 3 brown precipitate. Copper ions give you a blue precipitate. Those three are a good proof for iron 2, iron 3, copper 2. Then the ions that you cannot prove, like magnesium, calcium, potassium, whether you get a white precipitate or whether you get no reaction, then that does not help you. And all of these remain in excess. With the potassium ions, there's no observable change in either a little bit or loads. And then the bottom two, they do prove aluminium ions and ammonium ions. Aluminium ions give you a white precipitate. Can you see that? It dissolves in excess, learn that. Aluminium ions are the only ions that will do that. Ammonium ions, when heated, there's a gas given off. The gas smelt awful. And another way of saying awful in chemistry is pungent. So the pungent smell means an awful smell. The awful smell will turn red litmus, damp red litmus, it will turn it blue, and then you know that it's ammonia gas. And if you get that, then you know the ion was ammonium ion. And that's a good proof of ammonium ions. Finally, you need to know what's going on precisely. So I want you to know with copper ions, the copper ions react with hydroxide ions. With iron 2 ions, the iron 2 plus ions react with hydroxide ions. With iron 3, they react with hydroxide ions. With aluminium, they react with hydroxide ions. With ammonium, they react with the hydroxide ions. So fundamentally, you add sodium hydroxide because you're looking at the reaction with hydroxide ions. Ionic equations. I've dealt with ionic equations in previous videos. Ionic equations tell you what ions are reacting with each other, and they cut to the chase. They give you the reaction that's actually happening. So copper ions with 2 hydroxide ions are making copper hydroxide, and that is blue. It's a blue solid, and that's why you get that blue coloration. Iron 2, green solid, brown solid, etc. I put these in my own handwriting. There, blue, green, brown. They prove those ions. How about aluminium? Well, aluminium ions give you a white precipitate, and that white precipitate with loads of sodium hydroxide, that white precipitate will redissolve. There, look, redissolves. And sorry, there should be a negative charge here. There should be a negative charge here. I've left it out, and that's a mistake. So you need to put a negative charge there. This is an ion, AlOH4 minus ion. And then finally, what I showed you last, ammonium ions react with hydroxide ions. They make something called ammonium hydroxide solution. And if you heat that solution, ammonia gas comes off. If ammonia gas comes off, then the ion that must have been there was ammonium. So those 5 ions in that table, those 5 ions you can identify with the reaction with sodium hydroxide. I know the last 2 you need to kind of like do a special observation. The special observation is with aluminium 3 plus it redissolves, and with ammonium ions you need to heat the solution and test for ammonia gas. And then you know you've got ammonium ions. But those 5 ions can be identified, and they're the 5 ions I want you to learn that you can identify using sodium hydroxide solution. I know I've been whittering on for like 45 minutes, but next we're going to do flame tests. So ions like calcium and magnesium and potassium that you could not identify with adding sodium hydroxide, you might be able to identify them using flame tests. And that's my next video. I'm going to carry on from this point next time. See you then.